let's try to sketch the titration curve for a polyprotic weak acid. So I've chosen here histidine, and what I'd like to do is sketch the titration curve for 100 mils of 0.1 molar histidine as it's titrated with 1 molar sodium hydroxide. And we can also talk about which species are present when we get to pH 8 along the titration curve. So, to begin, we'll look at the 3 sites on the histidine molecules that can contain a proton that is removable, an acidic proton. There are 3 of them with pKa 1, 1.81, pKa 2, 6, and pKa 3, 9.85. The associated sites are as follows. This is the most acidic proton. It has the lowest pKa, this carboxylic acid group. So this one is associated with pKa 1 of 1.81. pKa 2 is associated with this site here, and I haven't drawn it with the proton on, so I've drawn it as pHs that are much greater than 6, where the basic form predominates. But if it were pHs less than 6, then there'd be a proton here. The final pKa of 9.85 is associated with this amino group here. And again, I've drawn it here in its basic form. Its acidic form would be encountered for pHs below pKa of 9.85. So pHs below 9.85, there'd be a proton here and a positive charge. So let's look at adding histidine starting at a low pH, starting at pH below 1.81, adding base, and observing as these 3 protons are sequentially removed. So here I've drawn the molecule again, and I want to start by just talking about the first proton to be removed from solution. So this proton at pHs around 1.8 is in equilibrium with the molecule here that's been ionized. So these 2 molecules, you notice they're identical except for this proton's been removed. And these 2 forms will be equal in concentration at pHs equal to the pKa of 1.81. So let's start to sketch out the titration curve. We know the titration curve is going to start at a pH below 1.81. That's something I just kind of defined. I said, let's start at a low pH and go to a high pH. So the solution is prepared at low pH. And the initial pH will be less than 1.8. And what I'm going to do is start adding base, raising the pH. And as I get to pHs around the first pKa, I'll have an equal mixture of these 2 forms. And I know one point on the titration curve will be where the pH is equal to the first pKa. And that will happen halfway to the first equivalence point. So here's the first equivalence point. Halfway there, I'll have an equal concentration of these 2 forms at pH equal pKa 1. Now, I can continue to add base, and when I do, I'll go over to the equivalence point of the first proton. So I'll completely remove the first proton. Remember, at half equivalent, I have equal concentrations of these. As I keep adding base, I get more and more of the base form until all of the acid form is used up. So at this point, the first equivalence point, all of the acid form is converted into the base form. But notice it's only for this first titration, this first proton. These other 2 protons are still attached. So let's continue now to add base. I'll get to this first equivalence point, of course, and I know that first equivalence point will be less than pH 6, and I know that because the second pKa is 6. So this second plateau occurs at pH 6. So let's look at that. As the pH is raised from 1.8 through 2, 3, 4, 5, and gets to 6, when that pH is equal to the second pKa, then I've removed half of these protons. Now I have a mixture of these 2 molecules. At pH exactly equal to the pKa 2, pH equals 6, there's an equal mixture of these two molecules. The first proton stays gone, it's completely gone, and now the second proton is being titrated. I can continue to add base, of course. So as I continue to add base, I'll sketch out more of the titration curve. So at pHs above 6, this proton will be completely removed. I'll get to the second equivalence point. At that second equivalence point, I've been converted to all this form. All these protons are gone. And that's the second end point, or the second equivalence point. It's kind of funny to say end point in a multiple titration. Equivalence point is certainly the better term. So the second equivalence point, it's going to occur at less than pH 9, but more than pH 6. So somewhere between 9 and 6, the two pKa's, I'll have the second equivalence point. At that second equivalence point, the form in solution is this. That is, the second proton has been completely removed. So let's continue. The next pKa is 9.85. That means the next plateau in the titration curve is at 9.85. So when the pH is equal to that pKa, I'll have an equal mixture now of this compound and this compound. Notice this proton is now being titrated, or this proton is being removed. And when the pH is exactly equal to the pKa, there'll be an equal mixture of these two species in solution. Now, I can continue to the third endpoint, and the third endpoint is where I've removed all of these protons, and the form in solution is exclusively completely deprotonated now. And that pH will be above 9.8. I know because this pH right here was around 9.8. Now let's look at that pH 8 position. We've sketched out the titration curve. And what we'd like to say is, at pH 8, which species are present in solution? Well, pH 8 is between 6 and 10. It's well above this initial pH. So pKa 1, that proton is certainly fully removed by the time we're at pH 8. So this is a negative ion right now. The other two species we have to worry about. Now, this proton here, this won't be removed until we're above pH 9.9. So that one's certainly going to be attached. So we don't have to worry about this pKa. We just have to worry about this pKa 6. We're about 2 pH units above that. So at 2 pH units above this pKa, what species is present in solution? And we can rely on our Henderson-Hasselbalch expression to look at that. So we'll look at the Henderson-Hasselbalch. We'll use the two forms in solution will be the protonated and unprotonated form here. This proton either attached or removed. The pKa is 6 for that, but we're at pH 8, so the difference between pH and pKa is 2. So the difference is 2, so 2 has to be log of this concentration ratio. And obviously that means if the log is equal to 2, there's a factor of 100, 10 to the 2, difference between this form, acid form, and base form. And we're on the basic side of the pKa, so it's the base form that has about 100 times more than the acid form. So these two forms, about 100 to 1. So clearly, mostly, the base form of this equilibrium is present at pH 8. Now, there's also some sodium ions from the sodium hydroxide that we've been adding. But there are no hydroxide ions per se, very, very low concentration of hydroxide ions, because all the hydroxide ions have been used up in converting the acid form to the base form. So the three forms predominantly in solution, there's really two forms predominant in solution. This, 100 times more common than this, and the sodium ions. Those are the ions present in highest concentration at pH 8.